maneuvers, the level turn when the aircraft turns in level position, or the pull up or the pull down maneuver, as well as the takeoff and the landing are important maneuvers. They usually come in terms of requirements. So when we do design, one requirement would be the maximum takeoff distance should not be more than a certain value, or the aircraft is capable to make a full turn within maybe 20 seconds, or the aircraft can be able or should be able to make a pull up that will increase the inertia load on it by a certain value. All these are requirements. So that's why it's important to have accelerated flights or to study accelerated flight performance. Today we are going to look at the level turn, the pull up, and the pull down. So let's start with this. Here is an aircraft turning in the horizontal plane. We are looking from the top and seeing the aircraft making that turn with a radius r. And as the aircraft does the turn, it was gonna tilt a little bit, right, for the turn. So if I look at the aircraft from the front, I will see the lift vector tilted with an angle phi. I will see the weights downward, and the aircraft is pointing right at you now. Now, since it's going in the circle with a constant speed, that doesn't mean it's going with the zero acceleration, because you have studied your dynamics. If a body is moving with a constant speed on a circle, what kind of acceleration will you have?
Centripetal.
Yes, centripetal acceleration. You're going to have acceleration pointing toward the center, and it has a value of
V squared over rho, or the
v
radius.
squared over. So if we write Newton's second law towards the center, so that's in this direction or in that direction here, it will can you mute yourselves? Okay. So writing Newton's second law in the horizontal direction, I'm going to have the mass times the acceleration. Here is the mass, and that's the centripetal acceleration v square over r, pointing toward the center here or pointing to the left in here. M times acceleration equals sum of the forces in the horizontal direction. Now, the only force we have in the horizontal direction is L sine the angle. If this is the angle, so it would be L sine the angle in the horizontal. So that's Newton's second law. And from sine, I can get sine the angle from here, okay? Or I can also I can write the equation in the vertical direction. In the vertical direction, there is no acceleration. Only the lifts cosine the angle is equal to the weight. So lift cosine the angle is equal to the weight, or cosine the angle is 1 over L over W. Okay. So that's for the turn. Now, L over W term is important and is defined as the load factor. So the load factor is defined as the lift over the weight. When the aircraft was flying straight and level, as we had before, this N was 0, was 1, L equal to the weight, so N was 1. Now that the aircraft is turning with an angle phi, N is equal to 1 over cosine phi. So it will increase. The more phi that you have, the smaller is this value, the more is the load factor. So it will not be 1. It can be 1.5, 1.2, 1.3, and so on. Also, I can find from here the radius of the turn. So I can separate R and I would know the radius of the turn. Now, from a design point of view, if you are designing a military aircraft, a fighter aircraft, for example, would higher values of R or lower values of R better? Again, the question. Yes. We always want lower values of R because lower values of R means the aircraft can make a sharp turn. And if it's making a sharp turn, he can now catch the tail of the aircraft in front of him, right? Or he can avoid, for example, a SAM missile being shot at him. So the sharper the turn, the better the design of the aircraft. So we want to reduce that R as much as we can. But in order for it to reduce, we must increase that N. So the load factor will increase. Okay. So if you increase the load factor, the radius will go down considerably. And we're going to see in the design how we're going to do this. Okay. Here is the angle. Phi is the angle with the vertical. So phi here is 30 degrees. And this is the remaining 60 degrees. At 60 degrees, if you substitute with phi, you will get a load factor of about 2. The more angle that we have, the more the load factor is going to be. And you can see it can increase from 1 to 1.5 to 2.5 and so on, depending on the angle that we have. Because the centripetal force are going to be in the horizontal direction, and the resultant lift will be along the resultant force that we have. Okay. Now, these are the only equations in here that require like derivation. From Newton's second law and the equilibrium in the vertical. Now, from this mix, if I substitute for L over W, I will get a variety of useful performance indicators. For example, if I say we already have the R, what about V over R? Well, V over R is the rate of turn, right? Because V equal omega R. So I can get omega by dividing V over R, and we already have. So that would be the expression for the omega. This is what would be the turn rate of the aircraft in radian per second. So it can go a full circle, which is 2 pi, within how many seconds? Well, it's a function only of N and V. I can also I can get rid of the lift and replace it with the drag because I have relationship between them, which is the drag polar. I can represent L in terms of G, and D is related to T. So at the end, I can get the load factor as a function of the drag polar parameter and the thrust ratio. You can get all sorts of important relations. So rather than the load factor here expressed in terms of L over W, which are not two design parameters, I can now have it as represented as CD naught, W over ST, which are design parameters. So we can change them and see the effect of this on the load factor. Now, I assume most of you have taken 220, so I hope you know exactly what I mean by the load factor. Do you have an appreciation of what we mean by the load factor, or I need to explain it? If you don't know what it means, okay, let me ask you a question to check. You are standing in an elevator and the elevator suddenly moves up. Would the load factor increase or decrease?
Increase.
Because the acceleration is downward, you will feel more weight on your feet. Okay. And if the elevator goes down, the load factor will decrease. You will feel less weight on your feet. Okay. Now, we already had an expression now for the radius of turn and the angular velocity. And just like any expression, I can find the maximum or the minimum value of that expression by finding the derivative, because it's just a function. So if I take the expression for R and differentiate it with respect to the speed, I can find when the radius is going to be minimum, because it's a good thing. If I have the expression of omega, I can differentiate it with respect to V and also find when this is going to be maximum, because it's a good thing. The faster the aircraft in the turn, the better. So this derivation, by taking the derivative and finding the expression, is requires 2 steps, and it's left as an exercise in the homework. So there is one homework problem in which you will derive these equations. Okay. You will start from the equation of R, differentiate it with respect to V, and finding out what is the minimum radius. Now that's a design requirement. So maybe in chapter 8, when we do a design of aircraft, it's required that has a minimum turn radius of maybe 200 meters, or a rate of turn of no less than 20 degrees per second, and so on. So I can use these as design parameters. And you can see that if I have the performance characteristics of the aircraft, it's just a matter of substitution of the numbers. There isn't really a lot of derivations here. So all the examples that had to do with the turn, just like example 6.2, are like direct substitution, just like we had with the A and so on. So let's see an example. I hope it will clarify the idea. For the same aircraft we have been looking at, the Gulfstream, let's say you want to find what would be the maximum turning rate. That means omega maximum. And the corresponding value of the load factor. And the velocity for that angle. Okay. So the expression for the turning rate for the W max is the one that we had. It's a function only of thrust to weight ratio, the drag polar, K and CD knots. All these we know for the Gulfstream. We have it for the Gulfstream. For the wing area, the altitude, the 30,000 feet, we have all these values for the Gulfstream. So it's just a matter of substitution. Density at 30,000 feet, wing area, wing loading was 76. The drag polar K was 0.08 and CD naught was 0.05. So this gives the maximum rate of turn of 0.25 radian per second. Omega here is in radian per second. But we don't appreciate radian per second very well. So if, yes, Hussein.
Yes, Q here is the dynamic pressure, or what?
Yeah,
It's
Q is
value.
the 1/2 V squared. It is the dynamic pressure.
Thank you.
And if you look at here, where did this let me go back one slide. Where did they come from? When we replaced the thrust by the drag has 1/2 rho V square, okay? And then it has the K and the CD naught, the parasite term as well as the induced term. Okay, so this is Q. Okay, this answers the question?
Yes, it does.
Okay.
Okay.
So having it 0.25 radian per second, again, we don't feel what's 0.25 radian per second. We need to convert it to degrees. So we will multiply by 180 over pi or by 57.3, giving us 14 degrees per second. So the Gulfstream can turn at 10 degrees per second, 12 degrees per second, but the tightest turn it can make is 14 degrees per second. That means it will make a full circle in the horizontal plane in about 25, 26 seconds, right? You want to make 360 degrees, so 360 over 14, it's 20 something, maybe 25 or 26 seconds. That's the full circle it can make. And this occurs at the load factor equation, which is thrust weight ratio over K CD naught minus 1 under root square. So the load factor will be 3.16. So if the pilot makes a very tight turn, the fastest turn that he can make in the horizontal plane, all the passengers inside the aircraft will feel a load factor of 3. That means they will be pushed against their seats with a force that's 3 times their weight. Okay? And this is typically what happens when the aircraft makes a turn. You feel that force against your seat. Any questions? Okay. Now let's look at the pull-up maneuver. In the pull-up maneuver, the aircraft now turns, but in the vertical plane, not the horizontal plane. So the aircraft was flying straight and level. Then the pilot suddenly pulls the stick. That means the elevator will move up, the nose of the aircraft will move up, and the aircraft will start doing a circle in the vertical plane. Let's say this circle with a radius r. At any angle theta, if I write the equation of motion or Newton's second law along the central direction as we did before, it will be mv square over r. That means mass acceleration is equal to the forces. The forces now is not only the component of the lift, it's the lift minus the weight cosine the angle. Lift minus weight cosine angle. So it's similar to the term, but we have that term in here. Okay. Now r, I can separate and get r on one side, everything else on the other. So here is the radius of term. If you want to have the angular speed omega, simply divide v over r. So it will be v over this expression. So I will get that one. So that's the simplest of all in here. So we have the radius of turn. Again, we want to minimize that and we want to maximize the turn rate. Okay. As you see, they are all functions of the load factor and the speed, of course. Now, the load factor, we need to have like a small discussion on the load factor in the pull-up here. That's another pull-up here. The pilot pulled the stick, acceleration upward, lift is up, weight is down, and the aircraft is pulling like this. Imagine that the aircraft is at the lowest position. So in this case, mass times acceleration is L minus W. That means the angle now is 0, right? So in this case, if I move the weight to the other side, it will be L equal the weight plus mass acceleration. And if I divide by W, that would be the load factor. So the load factor is 1, because this one will be 1 when I divide by W. I will divide the whole equation by W. This will be 1 plus V square over R, here it is, and M over W is G. So that will be V square over GR. So that's the expression of the load factor. Now, why did we put it in this form? Because now it's a function of important performance characteristics, just speed and R. A good airplane can make a turn at a high speed, small r, but that will result in a very high value of the load factor. And you can see the load factor will always be more than 1, 1.5, 1.2, 1.3, 2, 3, 4, depending on the V and R. Straight and level flight is the infinity, because the aircraft is flying straight and level, so the radius is infinity, so the load factor is 1. But for pull out of a dive, the load factor is more than 1. Can the pilot make a very sharp turn with a high V and small r such that the load factor becomes 10? Can he do that?
I think no, you can't.
Why?
If you want to tolerate the force,
You want to what?
يعني ما راح يقدر يستحمل الفورس.
Yes. The airplane can handle that. If you increase the speed, decrease the R, we can design the structure to handle that. But maybe the force will be too much for the pilot. Yes. Okay. So that's the other name that we have for the load factor, with the G forces, right? We call it a G force. So human bodies can withstand certain G forces, and we're going to have a look at them in just a second. Okay. Now look at this maneuver. It's the same as the one that we had, except that the lift now is pointing downward and the aircraft now is rotating, going up and then down again. Now in this case, the only thing that changes the direction of the lift. So you can expect that we're going to have only a change of sign in the expressions. We don't need to get the expressions again, just put a negative sign. Okay? So you put a negative, change the negative sign. It was negative, now it's positive. I'll get the expressions for the R and the omega. Also, the expression for the load factor 1 plus V square over GR, it will be 1 minus V square over GR in negative maneuvers. Now, So in a maneuver like this, in a negative maneuver, can the load factor be 0? From the equation, can the load factor be 0?
Yes.
Yes. If you pick V square over GR to be equal to 1, this term will be 0. And that means the person will be weightless in his seat. He will not feel any weight on the seat. Can it be negative? Yes. If this term is more than 1, N is going to be negative. That means a person on the aircraft will feel some force is trying to snatch him from the seat, take him from the seat. So that's why sometimes this negative maneuver can be done when the aircraft is upright or the aircraft is inverted. Now, to see this, I'm gonna just jump and talk about it like this. The same maneuver can be done if the aircraft is inverted or the aircraft is upright. See, this maneuver is very similar to this maneuver. Okay. In here, the weight is down, the weight is down. The acceleration toward the center, the acceleration toward the center. The lift is up, the lift is up to balance it. The main difference in here is what's the main difference between these two maneuvers?
I think the radius is constant and changed the radius.
The radius? No, assume the radius is the same. Assume this radius is the same. What's the main difference between this maneuver and that maneuver?
The direction of L.
Yes. Now, for an occupant of this aircraft, the main difference. Problem now is that here we are going to have the force that's pushing is going to be pushing towards, it's pushing upward, right? And here it's still pushing up. Well, it's the same, the centripetal force that we have. But here upward is towards the head of the pilot. But here upward is toward the feet of the pilot. Now, that makes a difference. It makes a big difference. Okay. In this maneuver that we're having here, due to the centripetal force, all the liquids in the body, including the precious blood, will tend to be pushed upward. That means the blood is going to accumulate in the blood vessels in the upper part of the body, including the brain. And since we have very thin brain blood vessels, there is a chance that some of them would rupture, explode, and that might lead to a fatal condition. So we cannot make this turn very tight, because the tighter the turn, that means the smaller they are or the faster the aircraft, the more is the load factor, the more is pushing the blood to the brain in here. We call this a negative maneuver or a negative load factor. By reversing the aircraft before going into the maneuver, it's the same force still pushing upward, but now the pilot is making it push towards his feet because the feet now is upward there. Now, isn't that dangerous? Well, it's a little bit dangerous because if you take all this blood and push it toward the feet, because the feet now is up there, you are taking blood from the brain. So, with no flow of blood to the brain, the pilot might be unconscious, right? Dizzy, then unconscious, but that's for a few seconds. When he recovers in here, blood will go back to the brain, things are fine, and he recovers. So it's very rarely that you see an airplane will do that negative maneuver in this way. It has to do it inverted so that we avoid the possibility of having a fatal condition with the brain. Does that make sense? This clear?
Yes, clear, Victor.
Okay. Now, this is the main reason why when you go on a roller coaster, if you have a roller coaster that's very tight turn, that means the radius is very small, you will always have the seats arranged such that the feet of the people are on the outside. So their heads inside and feet outside, because the blood now will push outwards. Okay. Whereas if you have a roller coaster, just like this one, such that the head are going to be on the top, feet at the bottom, the roller coaster, one, the track has to have a wide R has to be very large, and two, it has to go down as it goes up before it goes down again, because you don't want to have this fatal condition of negative load factor. Okay, so by reversing the aircraft, we are kind of making it a positive load factor again, rather than negative load factor. Okay. Now, where is that one? Now that's another application of the load factor. Probably have seen this maybe in National Geographic or something. The zero-G aircrafts. There is an aircraft 727 that's being adjusted such that it works as a zero-G platform. You can go and book a ride on the aircraft that will go with you up to 30 to 33,000 feet, and then the pilot will push on the stick. You see, that's a dangerous maneuver. That's the one that's going to generate forces pushing you upward. All the blood will go up and you will go up. But of course, he's doing it at a very large radius, very calculated radius actually, such that V square is exactly equal to GR. And if that's the case, then V square over GR is 1. That means the load factor is 0. So a 0 load factor means you are weightless. You don't have any weight pushing on the seats. So if they unbuckle the seat belts, they will be floating in the cockpit or on the cabin, on the passenger cabin. So you see the passenger just flying as if they are astronauts. And the reason for this, because the load factor in this case is 0, but it's only for a few seconds, maybe 20 seconds until the aircraft make the turn and then start to push downward again, comes out of the right. Okay, so that's how we generate artificial zero-G. Okay. Now, for us here, we should have like some limits on the load factors as designers, because as you mentioned, we cannot design for a load factor of 10. Humans will not sustain that. So, and if humans cannot sustain that, there is no point in making the structure strong enough for that. That will be just extra weight. So when we start looking at the structure, how far can we go with the load factor? Well, this is determined by the capacity of humans. You see here load factor 1, 1.5, maybe 4. It becomes worse at higher load factors. So these are the typical values, and there is no derivation for this. There is no calculation for that. It's just the average of human capacities. So if you are a passenger in a transport aircraft, regular passenger, it's expected that you can withstand positive load factors between 3 to 4. Beyond that, you might be unconscious because of lack of blood flow in the brain. But on the negative side, the more dangerous side, when the blood accumulates in the head, normal human beings can withstand to load factors between -1 and -2. So most transport aircraft are designed for a negative load factor of -1.5. That's an average. Now for fighter planes, where you have pilots more fit, more physically fit, they can withstand positive load factors between 6 and 9, and negative load factors between 3 and 6. Okay, and since for aircraft designers, you want to push the aircraft to the limit, these would be the limits that we design on for transport aircraft, and these are the limits we design on for fighter aircraft. And here are the limits for different kinds of other aircraft. You will always see that the positive values are more in magnitude than the magnitude of the negative values. Simply, the only reason why we have this is that our brains are in our heads. If the brains were in the feet, you will see these numbers flipped. Okay, It has nothing to do with aerodynamics. It has nothing to do with structures. It has to do with the fact that human beings are symmetric about the horizontal axis. Okay. Any questions so far on the load factors? Okay. Now, let me go one slide back. Now, with these load factors, we can start to define our loads on the aircraft. An aircraft flying straight and level will have a load factor of 1. The maximum load applied on the structure is 1. Okay. Now, but the aircraft will climb and turn and do these maneuvers. So what would be the maximum load to which the wing is applied? Well, it will equal the load factor multiplied by the weight. Now, if we look throughout the whole mission of the aircraft, what would be the maximum load that a certain part will feel? We call this the limit load or the applied load. Okay, so now we are starting to talk a little bit of structural terminology. So an aircraft, let's say, will taxi, load factor is 1, climb or turn as it climbs, load factor maybe 1.5, then it will cruise, load factor of 1, make a turn, load factor of 2, maybe a little bit negative maneuver, -1. What is the maximum value? Then that would be the limit load that we have. Okay. Now, from a structural point of view, we should not have any permanent deformation in any part of the structure under that limit load. Think of that limit load like the yield stress that you had in material science or you had in physics. Before the load reaches a certain value, there should not be any yielding in the material. So before the load reaches the limit load, there should not be any permanent deformation in the structure that we have. Okay. On the other hand, what if the pilot has to do like some maneuver that he shouldn't, increase the load factor beyond the value that was designed for whatever reason, avoid a missile, avoid a mountain, emergency turn, turbulence, whatever. What if he has to do that? We should give him some room, some extra safety. Okay? So the way we do this is we say, okay, we're going to take that limit load. Let's say we decided the limit load will be corresponding to a load factor of 4. We will design the aircraft for a load factor of 4. So that means the lift will be 4 times the weight. But we will add a little bit extra. We will multiply by a factor of safety, which is typically 1.5. So I will design the aircraft for a load factor of 6. 1.5 times 4 is equal to 6. Now, under the 6 or the 5, anything above the 4, I should expect some permanent deformation. Maybe the wing will be twisted a little bit. Maybe some of the rivets will pop out of the skin. Maybe some of the skin panels, the surface will buckle a little bit. There will be some fractures. There will be some permanent deformation. But at the end of the day, the structure will survive. There will not be fatal deformation. Think of the area between the limit and the design loads, just like the area between the yield stress and the ultimate stress in materials. You will have permanent deformation. You will have plasticity, right? But you will not have complete failure. Complete failure will occur whenever we reach the ultimate value. So that's why it's important to define the load factor. When we say these are my load factors, I should ask myself, are they limit load factors or design load factors? If they are limits, that means the aircraft should be able to go to load factor 2.5 or 3.8 and come back without no problems at all. But if something happened and the pilot has to go to load factor of 4 or 4.5, then I should check the aircraft afterwards for some permanent deformation. but again, the aircraft will survive that load as well. Our safety factor in the aviation industry is 1.5. We almost multiply by 1.5. This is considerably smaller than load factors, safety factors in other industries. For ME, for example, typical factor of safety would be 2. For civil engineering, it would be 4. And if you are designing like a dam, for example, something that's very serious, then maybe the safety factor can be 7. So depending on the industry, for aviation, it's just 1.5 because we worry about the weight. Weight is an issue. You cannot increase the safety factor considerably. Okay, sure. Any questions? Any questions? Load factors? G loadings? Next time we're going to look at the VN diagram, takeoff and landing, and that will be it for chapter 6. And so that will be Monday, inshallah. Wednesday, we will start look at the design. So that will be the end of the performance. I know it took some considerable part of the course, but we will put everything together. Chapter 2, aerodynamics, 3, propulsion, 4, 5, and 6 for the performance. And we're going to put everything together in a design next Wednesday. Okay. No questions?
Yes, it's clear.
Okay. So I'll be seeing you, inshallah, on Monday. Tomorrow, inshallah, you are going to see your grades and check if there's any warning for this course under your portal and for the other courses as well. Don't forget that. Okay. Shukran.
Thank you, Doctor.